Hello.
Yeah, now it
Um,
started now. So,
yeah. Welcome to the APRG seminar this week, and we are very pleased to have Luz Roncal. And I mean, she doesn't need any introduction to the Indian Harmonic Analysis Group, but anyway, he works in BCAM, Bilbao, and she's going to talk about what is that? Pointwise localization and weighted inequalities for Rubio de Francia square functions. Yeah, you can
Okay.
start your lecture now.
So thank you very much, Veluma, for the introduction. And yeah, once again, it's a pleasure to be again in Bangalore, although online. But yeah, I know very well the place, and I'm very happy. I've been very happy there, and I'm happy to come back somewhat again. So today I chose a topic that actually you will see in the last slide because I think it has a lot of Indian flavor because. Originally I was introduced to this problem by two Indian collaborators, Rov Srivastava, maybe he's there, and Rahul Garg. And we had quite a lot of fun some years ago trying to think about the problem that I'm going to present. And so what I'm going to report today is a recent contribution, say last August, that we did with my collaborators here in Bilbao. So they are Mikel Flores Amatriain, who was lecturing last month, and he's a student of PhD student of Yanis Parisis and I. Actually, Yanis Parisis is here. And Yanis is also a researcher in Bilbao at the University of the Basque Country. And the collaborator also Francesco Di Plinio, that is from Università he's in Napoli, Italy. So I will just make a first introductory part. Maybe for people in harmonic analysis, this will be very well known, or maybe not, but just to try to reach a more general audience, I will try to be a bit more general, and then I will explain the problem, say a bit of the history of the problem, the development, and then I will pass to the contributions. Okay. So that the second part will be more technical. I try just to summarize the main ideas. Sometimes if people are not experts, maybe it's more difficult to follow, but the point is just to have in mind which are the ideas behind the proof. So, okay, also I would like to say, although it will be in the last slide as well, that mainly this presentation and the nice pictures are due to Mikel, my student. He's very good in doing this kind of stuff, so I borrow from him. He was very generous to lend me the presentation and the pictures, so I just elaborated a bit, but the credits are for him. So I will start with first the most general situation. That is, I will explain what is a general square function. Okay, so we are going to consider a collection of disjoint intervals, and we will be thinking of the frequency space. Okay, so we have a function in space, and then we take the Fourier transform. So we go to the Fourier side, which it is called the frequency space. Or, and in this space in R, in one dimension, what I'm going to do is to put this collection of disjoint intervals. So in principle, just the only condition I will ask is that they are disjoint. So I will have new omega naught, 1, 2, 3, and then the same for the left. Okay. So what I'm going to do now is I will take one function, for instance, the function 1 in an interval, -1, 1, and then I take the Fourier transform. So the Fourier transform of this function, that is the sine x over x function, is just plotted here. Okay, and then what I'm going to do now is that, okay, in each of the frequency intervals, I'm going just to take the corresponding part of the Fourier transform of this function f equal 1 in the interval. Okay, so I will just define the projection, the rough projection in each one of these intervals by means of the Fourier transform like this. Okay, so the projection interval of the projection operator of the function in the interval omega k is defined by Fourier transform like the indicator on the interval and times the Fourier transform. Okay, so this is then once I do this, what I'm going to do is to take the square of all these projections, sum all the indexes case, and then take the square root of this quantity. Okay, so this is the operator TF. And this is, I will call rough function, because actually what I'm doing is that in each interval, I'm just collecting the part of the Fourier transform of the function by just cutting in a bit rough way. So this is the cut and this is 0, right? So here this is the cut, this is 0. So this is a rough way to select the interval. So, but I could do this, say, selection in a smoother way, and so there is a this BAM functions shouldn't be a bit overlapping, but I was not able to correct this, so just forget about that. So what I can do is just, instead of putting just a rough interval cut in each interval, I can just select it in a smooth way. Okay. So in some sense that, I don't have, I solve this continuity problem in some sense, okay? So again, I define the corresponding smooth projections by the Fourier transform in this way. And then I can just define an operator in which I sum all the squares of the projections, sum of the squares of all the projections, and they take the square root, okay? These are square functions. Okay, so which is the idea to consider this kind of operators? The point is that back to the original Littlewood-Paley theory, as we know, one of the important properties of the Fourier transform is that there is isometry in L2. But then, when P is not equal to, because of Plancharel, instead of Plancharel, what can we have when P is not 2? Okay, so this question could be reformulated in the sense that, okay, I have introduced these operators. What can I say about the mapping properties in LP beyond 2 of these operators G and T? Okay, so then the original square function, I would say, is the Littlewood-Paley square function. So the point is that the collection of intervals that we are taking are dyadic intervals. Okay, so we are taking this collection of intervals, and this will continue towards the origin, and then I'm doing the same thing. So I'm just taking each of these intervals, then I take the projection of the function in each of these intervals, take the square, sum all of them, and take the square root. Okay, so these are the pictures, and this is what I will define like Littlewood-Paley square function. Okay, and as I mentioned, this is the rough is a rough operator in this sense. So what is known? What is known is that this operator actually is the LP node of this operator is equivalent to the LP node of the function f. Okay, and this is true for p between 1 and infinity, not reaching the endpoints. For the endpoints, maybe I should refer to works by Tao and Wright and other people. Okay, so I will not enter into details, but this is not for Littlewood-Paley. So this is a very good substitute of Plancharel theorem for p not equal to. But then one can think of what is going on if you consider other kind of intervals beyond the dyadic intervals. So, for instance, if we consider intervals which are all of the same length, okay, so like the ones that are plotted here, I can do the same definition, the corresponding definition of the square function. And for this operator, for the operator in this case, what is known is that we have LP boundedness for a range of p that is greater or equal than 2 and less than infinity. Okay, so this is a result by Carleson and later revisited by Antonio Cordova. And actually, this is known to be sharp in the sense that you can find functions for which you don't have boundedness for p less than 2. Okay, so this result was still revisited by José Luis Rubio de Francia in 1983, and in this work, it's a beautiful work. He gives a lot of insight about what is going on behind this operator. So in order to prove the same result, he finds a very nice pointwise inequality that says that, okay, remember, I use T for the rough operator, okay, and G is the notation for the smooth operator, okay. So he considers he finds this pointwise inequality for the smooth operator, okay, by means of this is bounded by this is the maximal hard-readable maximal function, and then from here one can deduce that actually the LP norm, even with weights of the rough operator, is bounded by LP norm with weights of the smooth version, and then from this pointwise inequality and the properties of the hard-readable maximal function, one can deduce the boundedness this time without weights, but reaching all the range up to 2. Okay. Actually, the Rubio de Francia result, this pointwise inequality, there is an intermediate estimate here given by a convolution, an average operator, a one-scale average operator that actually, by using this estimate that I haven't written here, by using this estimate, intermediate estimate, one can get L2 boundedness with weights for weights in the Muckenhoupt class AP/2. Okay, so the point is that he is able to find this result in more generality, and then the next step is that what's going on if we consider an arbitrary collection of intervals as the beginning, with maybe the only restraint that the intervals are disjoint. Okay. So okay, this is the first. Remember the first slide. This is the most general situation, and then for this general situation, Rubio de Francia proves that these operators are bounded in LP for p greater or equal than 2. Okay. And this is actually the chain of inequalities. I will just explain a little bit of how it works. And when it comes to weights, and here is the very interesting thing, is that he also gives the version with Muckenhoupt weights in the class AP/2, but only for the range p between 2 and infinity. Okay, so p equal 2 is open. So just to give a glimpse about the proof, so again, Rubio de Francia, the approach is as follows. He reduces the boundedness for the rough operator to the smooth operator. Okay. Then for the smooth operator, this time in most generality, he manages to find this pointwise inequality, where now instead of having here the smooth operator, he manages to put the sharp maximal function. Okay, so this is actually something like this. Okay, and this is the sharp maximal function. This actually is also giving an idea that what is going on in the endpoint is some kind of BMO phenomenon. And okay, this
so
is
Luz.
Yes.
So what is the assumption on F here? Is an LP function or just any measurable? This
F is LP function.
For p greater than 2, right?
Yeah. No. Okay. Here, sorry. For p equal to, sorry, yeah. Thank you, Mona. For p equal to, the result is immediate by Plancherel. Of course, you are right. Of course, you are right. Yes. Then the boundedness in LP will be only possible when, yeah, you're right. Sorry, thank you. It will be only possible when p/2 is greater than 1, strictly greater than 1. Exactly. Sorry. So for f in LP for p greater than 2, so this is the approach. For p equal to, the result is immediate because of Plancherel, without weights. Okay. So okay, so yeah, so from this, actually, this is what I'm saying. Well, but this is with weights. So with this pointwise inequality, then as explained to you, no, one deduces the unweighted, but also the weighted inequality with weights in the Muckenhoupt class AP/2, but for the range P greater than 2 strict. So remark, no, then following Muna's comment. For P equal to, unweighted is immediately because of Plancherel. For P equal to, weighted is not known because now the structure, the general structure of the intervals doesn't allow to look at your operator G as some single scale average operator that was the trick that Rubio de Francia played in the previous situation and which allowed him to reach the endpoint P equal to with weights, okay? So this is the state, and of course the question is what's going on with the endpoint P equal to, right? So, okay, it turned out that this was a very interesting problem. Rubio de Francia conjectured that, well, the weighted bundle should be true for weights in A1, okay? And which is the situation? Well, Rubio de Francia himself in 1989 proved the conjecture when you have power weights, okay? The proof this is in a paper this is famous transfers for radial multipliers in Duke, and actually if you look at the proof, it's quite obscure. And Rubio de Francia himself says that this is not the proof I would like, but you know, this is it. I cannot do anything else. And but later Carbery, by the way, I will just make a small digression about Rubio de Francia. Rubio de Francia passed away in 1888. Actually, this result comes up, was published after his death. Then there was a volume in Publications journal about the memory and the work of Rubio de Francia, and in this volume, Tony Carbery gave some result, but in particular gave an alternative proof of this result by Rubio de Francia in a actually quite elegant way, but very much ad hoc for power weights. So this is maybe the last year in which the most important information was given towards the conjecture, and it was not until 2014 when Sebastian Kroll gave information about the endpoint, saying that okay, what you have is weighted with type. Of course, the strong type is still open, as far as I know. So just one digression, I would like just to explain a little bit, because Rubio de Francia's name has appeared again and again and again, and I would like to say that this is a very important mathematician in Spanish mathematical community. In particular, was my grandfather, but actually it's a pity because he passed away very, very young. And he did very important and deep contributions to the field of Euclidean harmonic analysis. He had several students, some of them were very famous, and actually he was one of the, I don't know how to say, the ones that made possible in Spain that the harmonic analysis, especially Euclidean harmonic analysis, was widely developed. So this is like a small tribute to this person. Okay, so what else? So
Luz,
yes.
no,
Yes.
Back to your previous result. This thing. What did you say about the endpoint here? This,
here.
that
That
you have only weak L2, right?
Yes, exactly. Weak L2, and this is positive. This is positive. The question is that what's going on with the strong type? This is open. Okay. This is actually this is the conjecture by Rubio de Francia, but yeah, and this is widely open apart from these results, and probably some that I will mention today that, well, there are small contributions only. So okay, there is another way to look at the Rubio de Francia square function, and is via a time frequency approach. Okay, so time frequency analysis now, well, also very well known, tries to take into account the localization of a function both in time and frequency space. Okay, so you what you do is to well, decompose this time frequency plane into tiles. Okay, so so it's space components, time components and frequency components are dyadic, and but the important thing is that you have to decompose them in such a way such that in each tail the uncertainty principle is maintained. Okay, so essentially this is what is saying this. Okay, these are ij and these are w omega. So okay, you decompose. This is something called tile. So this is a product. We are doing all the time one dimension, and this is R2, right? So this is a tile. It's a product of an time and a frequency interval, keeping the uncertainty principle. And the idea is that with these decompositions, you can find certain special functions which are perfectly localized in frequency and very well localized in time. Okay, in the sense that most of the mass is around the time interval, and then there are some tails that is in principle are nicer to handle, but of course this is the key point in time frequency analysis, how to handle the tails. Okay, so this is what I'm saying this here. Okay, so so then an alternative approach to this Rubio de Francia problem by using time frequency analysis was, as far as I know, first proposed by Michael Lacey in 2007. Okay, so the main idea is just to give me the Rubio de Francia square function and discretize it, discretize the operator in the sense that you are reducing your operator to what is called a wave packet square function. Okay, something that could have this kind of aspect. Okay, so we are localizing in time, and here these are these functions that I mentioned here that are perfectly localizing in frequency, very well localizing in time. Okay, so then if you want to study the Rubio de Francia square function, you have to analyze the corresponding let's call model operator. Okay, so so this is model operator. Okay, so this is the idea by Michael Lacey. So he developed this idea in a paper in 2007, and with this approach he recovered the same results as Rubio de Francia in 85. Okay, nothing else. Okay, it's just it's another way to try to understand this operator, although it's not giving better results. But it's a nice, it's a very nice point of view, and actually, this is the point of view that with Rahul and Saurav Srivastava we used some years later. Before that, I would like also to introduce sparse operators because well, this will be also part of our contributions. Also, I guess that people in Euclidean harmonic analysis are very used to these kind of operators that have been very important recently because they have, in some sense, has been revolutionary in the way of looking at Calderon-Simon theory. So essentially, this is a very brief summary of the situation. Is that so? We have a collection, in this case, intervals because we are in one dimension. We call a collection of intervals eta sparse. Eta should be a number between 0 and 1. If for every interval there exists a subset EI, such that is the measure is comparable, and then all the collection of all these EI are pairwise disjoints. Okay, so just some notation. This is the notation I will use for the averages. These are the p averages of a function f. Okay, and then a sparse operator or a sparse bound for a certain operator t will be an inequality pointwise. Okay, of this way. Okay, so. I think, yeah, even in India, in Bangalore, there was a nice lecture some years ago. We can talk about sparse form as well. So we say that an operator is bounded by a sparse form if we have an inequality of this way. Okay. Okay. So. The relation between these two forms is that if you have a pointwise sparse for an operator, this is stronger than a sparse form. Actually, by some duality argument, you can deduce sparse bounds for the sparse form if you have some bounds for the sparse pointwise formula. Okay, so this is stronger, and actually one of the points of representing singular integral operators or other operators in terms of sparse forms is that there is a very easy and standard way to produce immediately weight and strong LP weighted estimates. Okay, so in some sense, coming back around this old problem by Rubio de Francia, where the main operation is that what is going on for weighted estimates in L2, it could make sense to see if one can look at the operator from the point of view of sparse operators and see what they are saying. Another thing that I didn't mention is that, of course, sparse bounds give weak and strong LP weighted estimates, but also in a quantitative way, in the sense that they give information about how the characteristic of the weight is appearing in the corresponding estimates. Okay, so also this motivated a little bit to look at this approach, because maybe depending on how is the behavior toward the endpoint of these quantitative estimates, maybe we could have something. Okay, so with all this circle of ideas, there is when I visited actually Veluma in 2018, I went to Bhopal for a couple of weeks, and then I was working with Rahul Garg and Saurabh Srivastava, who introduced me to the problem, and actually what we proved is that well, we can have a sparse form domination for the Rubio de Francia square function, which is of this type. Okay, so here we have a 2 average and we have a 1 average. This is not precise because actually this should be a vector valued sparse form, but just to have the idea, it's okay. So from this sparse form domination, the standard results are giving us information about the quantitative weighted bounds for p greater than 2 and for the weighted weak type. Of course, this is not giving information for the LP strong, for a strong L2 with weights, because actually it would be very, very cheap way to prove the conjecture. So that was something that we expected. And yeah. So the point is that I would like just to mention 2 things. So first, this sparse form is sharp in the sense that we cannot lower this index 2 towards 2 minus epsilon, because then this would imply unweighted estimates for the operator for p less than 2, that we know that this is not true in general. Okay, so this is sharp in that sense. And also what's happening here. So we do not know if these quantitative estimates are sharp. In which sense? For instance, looking at the strong, the maximum here is 1. This is 1 when p is greater or equal than 3. And actually this is sharp. Okay, but we do not know if this exponent is sharp for the interval p between 2 and 3. Okay, if you see now, when p tends to 2, this blows up. So if this would be sharp, this be giving the essentially almost the conjecture, right? Because he's saying that, or giving an intuition for the conjecture, because this is saying that as long as you are reaching the endpoint, this is blowing up. So maybe you cannot expect a strong bound. But we do not know if this is a strong or sharp or not. Also, the quantitative weight for weak is not known if it is sharp or not. It's also interesting, will be interesting to know the sharpness of this quantity, because, for instance, this logarithm here, if you look at different or similar situations for other operators in Euclidean in harmonic analysis, like singular integral operators, this logarithm has been proved to be there for the endpoint p equal 1. And actually, this is also giving an intuition that because for the singular integral operators in p equal 1, you don't have a strong. So this is also this. If we can say something about this, if this can be removed or not, maybe could give some information, intuition about towards the conjecture. Okay. So this is the point, and which is our contribution. Our contribution with Mikel, Francesco, and Yanis is that we managed to lower 1/2 this exponent. Maybe this is one of the contributions in our paper. And we also proved some new sharp weak LP bonds with weights for p greater than 2. Okay, so this is the contribution, and then now how? The way to prove our contribution, what we prove is actually that we can pointwise sparse dominate both the square function, the Rubio de Francia square function, and also the smooth version of the Rubio de Francia square function. Okay, so the theorem is this one. So there exist sparse operators that I will define soon, such that the Rubio de Francia square function and a smooth Rubio de Francia square function are pointwise dominated by these guys. Okay, so as a corollary, then we can produce again quantitative weighted estimates, and maybe I will just emphasize one of the most interesting, that is that we are able to lowering by 1/2 this logarithm that appears in the estimate that we obtain with Rahul and sort of. Okay, so the main idea is here. So the way is that first we pass to the smooth operator with a loss of 1/2 here. And then we use essentially known results that still we don't know if they are sharp, that produces the extra A1 to the 1/2 and the logarithm to the 1/2. Okay. So the main strategy will be just, okay, how to do this? We will start with the Rubio de Francia square function. We reduce the situation to time frequency square operator, alike Lacy did, or alike with Sorov and Rahul we did. Okay, this you will take it for granted. Of course, this is part of the proof, but I will not enter into details. And then once you have this model time frequency square operator, you deduce pointwise sparse bounds for that. Okay. Once you have the sparse bounds, you deduce weighted bounds for the sparse operator smooth, because we know how to pass from here to here with a loss of 1/2. But then the estimates, the weighted weak type estimates for these operators are better than the ones we had just from the sparse from by Rahul, Garhan, Sarov, and I. Okay, so yeah, this is what I just mentioned. That one has to quantify this difference when you pass from rough to smooth, and then yeah. Okay, so the rest of the talk I will just give technical ideas of how is this proven, and then I will just finish with a couple of comments in 2 more situations. So, okay, the sparse operators that I mentioned in my theorem are these ones. So for the rough, we will dominate by this kind of operator for p equal to. Okay, so we will have this will be the corresponding for the rough, and for the smooth, we will estimate by such a sparse operator with p equal to. Okay, so this is just what I mentioned. Okay, so these are our results, being TP or T2 and G2 coming from here. Okay, how to do this? I will just present the idea of how to get the estimate for the smooth. Okay, the rough is even a bit more technical, and just for the sake of presentation, I will just reduce to the ideas of the proof for the smooth. So there is one important concept that is present in our proof that actually is also quite typical in dyadic harmonic analysis, sparse operators, and time frequency analysis, that is called Carlson sequences. Okay, so we will say that a sequence indexed in dyadic intervals is a Carlson sequence subordinated to a function g, given an interval g, if we have this estimate here. Okay, so I am summing over all dyadic intervals from the dyadic intervals related to y. And here, this average is something special, because this average here is an average, but in which I am just introducing a smooth bump. Okay, so this is the situation. Usually, the average without this cross is just the average on an interval. But what I'm doing here is just to smoothing this and taking all this decay, because essentially what's going on, and I will just, yeah. So what's going on is the following. Since we are in a model time frequency model, and as I mentioned, no, the point with the time frequency model is that your functions are well localized in frequency, but they have these tails in space. So essentially, this decay here are coming from these tails that one has to take into account when one deals with a time frequency model. Okay, so then we introduce this definition, and the key proposition will be this one. It's an abstract proposition saying that if you have a Carlson sequence subordinated to a function g, then you are able to have this pointwise inequality, where this T1F is the operator, the sparse operator that I just introduced here, right, with P equal 1. So if one is able to, yes?
Hello. In
Yes.
this definition of GPI toggle, so you have really taken chi I to the power 10 to 10p, right?
Yes. Yes.
So how does it affect? Because chi I is an indicator function.
Because chi I
is an indicator function, right?
Chi is it's an indicator with some decay. That is the important thing.
Oh, sorry.
Yeah.
Chi I is.
Yeah, chi I, yeah. This is the important thing actually, because this is coming from your time frequency model, where the function, the wave packets have this decay, and yeah. So yeah, thank you. So okay, so we will prove this abstract result, and then with this result at hand, I will explain how the proof goes. Because as I mentioned, you start with your Rubio de Francia square function. Well, actually, I'm looking at the GF, okay, I thought. So one is able to reduce this to a model operator written with some wave packet as square functions, okay? This work, take it for granted. One has to do it, of course. And the point is that we will prove that that this is bounded by this time of sparse operator that can be rewritten in terms of T1 like that. Good. So just take a square. So our goal is to get this estimate, or equivalently to have this estimate, where these are the wave packet time frequency model. So now let me rewrite this, because here we are summing over all tiles, okay, from the decomposition. So actually we can write this sum as sum over all tiles I times omega, where the intervals are coming from a dyadic family. So what's going on? So this guy here is actually the form that of this operator here. So and the inner sum are representing the sum sequence. Okay. So yeah, this is what this is again. So this is the IAI. Okay. Good. The point is that by nice properties of almost orthogonality of these wave packets, one can prove that indeed this sum is a Carleson sequence subordinated to f squared. Then our proposition will produce this bound here. Okay, so a smooth operator reduced to time frequency analysis, right in a proper way, and then thanks to the properties of almost orthogonality of wave packets, what one has is that this collection here is a sequence, Carleson sequence subordinated to f squared. Thanks to the proposition we just proved, then we have the estimate here. Okay, so then the goal is to prove the proposition. Okay, so this is the point. Okay, this is the point. Actually, yeah. What shall we do? So I will just explain the ideas. Okay, so let's take the function and let's take okay, these estimates are proven for compactly supported functions. Okay, then one can extend to LP functions. This is also something standard, but so we will deal with supported functions. Take the support of the function into a cube, dyadic cube. Take a little bit. I mean, take the least. Sorry, the largest dyadic interval who is contained in the support of the function. Yeah, and now split this sum into dyadic intervals such that you have to see which intervals are contained in this Q support and which are not. Okay, so actually for this, essentially what you have to do is these are encoding the tails of your time frequency model, and this is the main part. Okay, now it's time of hand waving, but you know, here are the details. So how to deal with the tails? Okay, so for this part, since we know that our coefficients AI are Carleson sequences subordinated to f squared, the Carleson condition says that we have this estimate here. Okay, then you can take the sum. No, it's okay like that. Yeah. So now the thing is that we don't want to have this kind of average with these bumps. Oh, sorry, with these nice decaying chi's, but we want to have a true average where the average is taken over some Q's that will be part of a sparse collection. Okay. So how to do this? Well, this is the situation. We have the function G supported here. Here is the biggest dyadic cube containing the support. And then I is not contained in the cube, but we have a chi that is something like that. So what we have to do is to find some ancestor of Q, some bigger cube that contains Y, so that in this ancestor, actually, we can just essentially neglect the rest of the tails. So this can be done in a finite number of ancestors, essentially because there is a big decay here, and at some point you can just get rid of this decay. So you can find some certain ancestors so that you, of course, here is the tails. You can dominate by this quantity, and these ancestors or these Q's are part of a sparse collection, so that the properties of sparseness follow. Okay, so this is for the tails. Yeah, for some ancestor. Yeah. So the main term, remember, that is when the I is inside the cube. Okay, yeah, this situation here. So in order to prove the estimate we want, actually this is something standard for say a sparse theory. So we use a recurrent iteration argument that actually is a sort of stopping time argument. So it's very well known in harmonic analysis, but with a certain and suitable stopping conditions. So start with a Q, take this Q, put it in the sparse collection, and now from among all subcubes, choose those ones, choose those maximal stopping intervals in the sense that this condition is satisfied. So this stopping condition is actually involving this Carlson condition, but just the other way around, okay? So take the maximal stopping intervals so that you don't have this Carlson condition. Okay, so actually for the green ones, there the Carlson condition, or thanks to the Carlson condition, you can find that these Qs are satisfying the sparsity, one of the sparsity conditions. Okay, and actually, since we are in the other cubes, we are also having this kind of estimate. Okay, that then this kind of estimate we know how to deal with to obtain the corresponding averages without this guy here. Okay. So iterate, now take the children, do the same, stopping time condition, and then iterate, and you can, in each step, add the corresponding Qs to the sparse collection, and then you can conclude the argument. Okay, this is the main idea. Okay, so I have 5 minutes, maybe?
Yeah.
Oh, well, okay. So then this is the main idea, no, to get these sparse estimates. And now, what about the weighted bounds? Once we have the sparse pointwise domination. Okay. So in order to get for the smooth operator, okay, one needs to deduce estimates for this pointwise sparse operator. Actually, as I explained in previous slides, this can be written in terms of T1S. And for this T1S, there are classical results or standard results giving some precise quantitative weighted estimates for strong and for weak. Okay, so they come from there. But then for the rough operator, okay, so how to obtain quantitative weighted bounds for this kind of operator? This is in general it was not known in the literature, and someone had to do something else. So the point is that what we did is to pass or relate this operator to G2S, for which we have the estimates. But as mentioned several times, we need to devise some idea to pass from here to here, and this will also cost us some quantitative extra loss. So the way to do this is by means of a good lambda inequality. Okay. So I will just explain in the next slide, and this good lambda inequality will allow us to do that via the weighted norms. I will explain in a moment. So in the sense that we will be able to transfer estimates for G2 to the estimates for T2 with the extra loss. Okay. So okay, this is the good lambda inequality we prove. So we are relating. Actually, this is general for p between 1 and infinity, taking 1. So we prove this kind of estimate with quantifying the loss, okay? And actually, by again standard or Euclidean harmonic analysis reasoning, you can deduce a weighted estimate. And here the loss is quantified. Actually, this loss is essentially coming from here. Okay. So, okay, there is something important to say here. The important thing is that to prove this good lambda inequality, to prove that one needs a pointwise inequality. We don't know how to elaborate such a good lambda inequality if we just have a sparse form inequalities. That, of course. With a weaker assumption, then you have the same result. Okay, so we don't know how to do that. Probably, maybe it's not even true, but okay. So the inspiration for these inequalities comes from the so-called Chan-Wilson-Wolf inequality, that maybe was initially stated for martingale square function. So it's an elaboration of these kind of ideas, but in our setting. Okay, so just this is like to put all the information, everything that I mentioned together. So this is the result. Okay, here we have, so 1/2 for all of them. And how to do, and as I mentioned, the estimate is sharp up to this logarithm term. That would be very nice to see if this is sharp or not. Okay. The proof is as follows. Start with the Rubio de Francia square function and then use the Pointwise sparse bound. For this, thanks to this good land inequality, we pass to the smooth version with a loss. And actually, you can just rewrite this operator or this norm like that because of the corresponding definitions. And now here, for instance, one can use standard results by Frey and Mirai, that, by the way, we don't know if they are sharp, to conclude the estimate we have. Okay? So, and then just rewrite again this norm as an L2 norm. So this is the result. So just two more comments. Actually, with this, not with these ideas, because this is something different. So we didn't use a sparse domination, nothing like that for this. We use the time frequency analysis models, or actually time frequency model, time frequency approach. So for the Walsh Rubio de Francia square function, like involving hard functions, actually one can get this estimate, the strong estimate, and this its estimate is sharp. Okay, so the conjecture is true for the Walsh Rubio de Francia square function. Okay, quantitatively sharp, it can be proven. And the main point is that for this, you can see it like a time frequency operator, kind of operator. But in this case, you don't have tails. You have orthogonality, there is no tails. And we think, of course, that this is critical in the proof. And here is where we are losing information. Okay. We also can confirm the conjecture by Rubio de Francia in a more general setting as he and Tony Carey proved. So actually, for even and radially decreasing A1 on the real line, the conjecture is true. And this is the quantification. And to be honest, now I don't remember if we thought that that if this is sharp or not. I don't remember, but I should check. Okay, so this generalizes the case that I mentioned before. And again, of course, the proof is highly dependent on this feature of the weights. Okay, but just to give some heuristics about these two cases that in some sense one can look at them in a unified way that can give some intuition. So the idea is the following. No, start with the corresponding time frequency model and write the L2 weighted norm with a layer cake decomposition. Okay, so you write your model like this. Okay, here are the level sets. Just rewrite the corresponding sum in terms of the maximal elements of your level sets. Okay, and then we can actually bound this part like an L2 norm times the corresponding chi I star, that are these functions with decay. So what's going on? Okay, so then our estimate was reduced to this. And of course, if we are able to control this by the weight, we are done. Okay. No, this is what's happening. So what's happening? Actually, if your weight is even and radially decreasing, you can cook up and you can actually get the estimate you want. Great. But also, if now we come back to the worst case in which I mentioned that the point is that you don't have tails, this chi is actually an I star. So the rough interval and 0 everywhere else. So in this case, so put here I star, actually you can deduce immediately that this is bounded by the weight. Okay, just actually by definition of layer cake. So, well, yeah, so this is all. These are all the results. I would like just to thank you for your attention. And yeah, as I mentioned, I want to also thank Mikkel for nice presentation pictures, and Rahul and Slof for introduce me to this project.
Thank you very much for a very nice talk on this interesting topic. Now maybe we can have some questions from the audience.
I have two questions. All these results were real line, right?
Yes, real line.
So what happens for higher dimensions? Are there any results?
For which? High dimensions,
instance,
yeah.
For instance, from the starting, you are really mentioning results 1 hour, right? Can you go back to your first or second?
Can you repeat? I mean, the sound is back where to where?
What I am saying that you, whatever results you have mentioned, these are really for real line, right?
Real line, yes, yes, yes.
But are there analogs for in higher dimension?
Yeah. Okay. So thanks for the question. There is almost contemporary to Rubio de Francia result in '85. There is a result by Journet. Also, I think it's '85 actually, and he proves estimates for the square function in Rn. And if I remember correctly, it's like a type of a product type operator. Okay. Beyond that, I am not aware of other results. I should, you know, this is dangerous, okay? Because one has to let me look. What is it? 1 second. What is Michael Lacey? Michael Lacey, yeah. Okay, so I think that in this paper, Lacey mentions about higher dimensions and mentions a paper by Kwang-Hwa Shu, whose name I'm probably writing incorrectly. And I think Kwang-Hwa Shu also gives some results in higher dimensions, probably related to the square Rubio de Francia function. Be careful, because Lacey says that he proves the conjecture, and this is not correct, okay? But probably these are the two, yeah, maybe the two, Journet in '85, and probably Kwang-Hwa Shu, I don't know, in the '90s. One should check. Maybe these are the only cases in which there are some higher dimensions in this spirit of Rubio de Francia square function are known. But maybe someone from the audience knows more than me, but I don't think nothing else is done.
I have a very simple question in the beginning. Actually, whenever you really broke that R into dyadic interval.
Yeah.
So you said that TF is comparable to really something like, yeah, this is the. So means, but for the other intervals, so it is less than equal to, right? This result.
Yes.
So what makes special to these intervals, to dyadic interval, so that it is really becoming two-sided? However, for other intervals.
Okay. Yes. Thanks again for the question. I should study more, because I remember, but very badly, these things. For the converse, probably even Rubio de Francia, for the converse like this, no? FF, LP, TF, no? This is what you wanted. Rubio de Francia also says something in his paper. Okay, there is some information, but yeah, I don't want to say anything else, because I will tell something that is not true. But yes, Rubio de Francia also says something about the converse. Okay, and I mean, I don't remember exactly which is the range, and if it was a vector value, then but you can see something there. Yeah. But you don't have the same thing, right? The point is that the converse actually works for an interval between 1 and 2, and so they are not really, it's more like one dual of the other, not complementary, or just giving this comparability. Yeah.
I don't have more question.
Are there some more questions? Yeah, if there are no more questions, let's thank Luz once again for a very interesting talk. Thank you very much.
Thank you very much.
Luz, we want to post this video in the YouTube. It is okay or?
Yeah, it's perfect. No problem.
Thank you.
you.
Thanks. Yeah.
Hi,
Yes.
Luz.
Hi, hi, Soro.
It is very nice. I mean, this development.